Hi and welcome back to a new video. Today's video will actually only be available in English simply because we're featuring an Intel interview which I was offered by my German Intel rep a few days ago during the preparation of Intel Accelerated, because I had some questions which were like manufacturing related, and he said maybe I just hook you up with some Intel engineers so you can discuss this further. And we're talking about some very skilled Intel engineers. So I had the opportunity to talk to Sanjay Natarajan, who is Senior Vice President, Co-Director of the Logic Technology Development Team, and he was in lead of the 14 nanometer process node development. The second engineer is Babak Sabi, who is the Corporate Vice President and General Manager of Assembly and Test Technology Deployment, basically working with everything that's packaging related. Before we get to the interview itself, I want you to keep some things in mind. First of all, we're talking to engineers, we're not talking to random marketing people. I only had a short time frame available where I could ask questions, and obviously I cannot ask questions which are related to future and unreleased products, because simply the reply would be they cannot give any kind of statements to unreleased products. That's why I asked some questions which might be related to products in the past, which I just asked out of personal interest, and I thought it would be interesting for you to just also get this additional information. And before some tinfoil heads get back out, no, this was not paid. This is not a paid advertisement. So first of all, I want to thank you both for your time and the opportunity to ask some questions to you. That's actually a big honor for me and a pleasure to be able to talk to you. So thank you also to Florian for arranging it. And there was a lot of discussions going on, especially after last week's announcements. And I want to point the first question to Sanjay about the fact of dropping the nanometers and going to like a new naming scheme of like the nanometer from 10 nanometer to, for example, Intel 7. Since you're also a member of the Institute of Electrical and Electronics Engineers, I was wondering when I was looking at the announcements, if you as a company, especially Intel, if you were thinking about is there a way to connect with like other companies to find a solution, to have something which is more, let's say, technical, to check out the area, the transistor density, switching speed, maybe power consumption, to come up with something that is comparable within the different process nodes? Or what was your like opinion on that?
Yeah, thanks, Roman. Great question. And first of all, thanks for having us on your show. Really appreciate it. Let me give some context, if I can go back a little bit and then sort of walk up to where we are now on this node naming changes that we just announced. If you go back far enough, maybe 30 or so years, the name of the node actually meant something physical. It was really tied to the gate length of the transistor. If you have if your audience has an electron microscope in their garage, they could have taken a chip back then and cut it and seen that if we say 0.35 micron, that you would find that the gate length is 0.35 micron, and that made sense. And then gate length made sense for a couple of reasons. First of all, it was a good proxy for density, because if you're going to make higher density, you got to shrink the gate length as part of that. Also, because back then we were doing sort of classical scaling, so we were getting more performance and lower power also by scaling the gate length in the era of what we used to call Dennard scaling. So that one number kind of reflected a lot of figures of merit. It reflected area and density. It reflected transistor performance. It reflected energy consumption, all really in one number. More like about 20 years ago, that relationship sort of broke down. We really finished classical scaling, and we started to get performance per watt with other techniques like strained silicon, like high K metal gate. And so that one number wasn't really a good proxy for for all of the figures of merit. So what the industry sort of started to do was disconnect the number that the node was called from physical features that you could measure. And that's been true for a long time. So when we say, Intel 10 nanometer, really that's not reflecting anything that's 10 nanometer physically on the chip. Yeah. Right. So that's kind of the back history on this. And that divergence has kind of taken place. And we're at the point now where we, Intel, are having to explain, when we say 10 nanometer, we and experts like yourself consistently have been saying that's the same as Foundry 7 nanometer. So this is really, for us, we need to give a meaningful framework to help our industry partners, to help our customers, especially now that we are starting a foundry business, restarting a foundry business, we need to have meaningful names that our customers can say, okay, and this is how I compare you to whatever else is available to me. So we've always been open to the idea of working together in the industry to come up with ways to benchmark transistor density, switching speed, power consumption. But I'd say there's really not been an appetite in the rest of the industry for this.
So it's like you were open to it, but for example, I don't know, like Samsung, TSMC, or whoever, they were like probably not interested to have something that's globally comparable, or.
I think to the best of my knowledge, you'd have to ask specific other companies, you know, their perspective. But you know, my perspective is yes. And in fact, we really tried to stay even at least true to the spirit for the longest time, where we, you know, at least each node number changed by a specific amount, and it reflected a specific intention around density and performance per watt. I think we were really the last big semiconductor company to at least exercise that in spirit.
During Intel Accelerated, you presented some very interesting new technologies, especially looking forward to 20A with PowerVia. Looking at this, I was very absolutely fascinated because when I was studying everything like this, it was very basic silicon manufacturing and just from one side. But how are you able to manufacture something like PowerVia? Because it looks to me like it has to be manufactured from both sides of the wafer, or can you give more details on that, how it works?
Yeah, a little bit. Let me maybe just for your audience explain PowerVia a little bit. So today, conventionally, you have a layer of where your transistors reside, and then you have your interconnect above it. That's miles and miles of wire, mostly made out of copper. And it includes both power delivery to the transistor, so power and ground, as well as signal routing lines that connect transistors together. We're taking all the power delivery off of the top and putting it on the backside. So the power will be delivered to the transistor from the bottom. The signal routing will be done still on the top. That has a couple of important benefits. First of all, when you free up that space on the top, you can now, if you wanted to make those signal lines faster, so lower resistance, lower capacitance, you have room to do that. If you wanted to pack everything closer together, you can do that. Another significant advantage, and I think your audience would really appreciate this, is now you can get power to the transistor with virtually no IR drop, virtually no voltage droop. And I think this is tremendous for, you know, power efficiency. And really, you'll see a huge benefit in the space where you're using relatively higher voltages. You know, I imagine a couple people in your audience are interested in things like overclocking, right? Yeah. So this is where we're tremendously proud of this technology. Now, to your exact question, I have to tell you this is a proprietary process. We're really proud of the inventions that have come together to enable PowerVia. But you know, proprietary means we're really not explaining to people how we're doing it. I think we're going to have to let our competition figure it out for themselves if they can.
Okay, I was expecting actually that, because it seems to be a very a difficult technology and nothing you would come up within one day. So yeah, it's a very impressive piece of technology, and I'm looking forward to see that in action, especially as you said, under overclocking conditions. Especially we're doing a lot of liquid nitrogen overclocking stuff, and power delivery is always one of our most important things. So that should be very interesting for us. When we were talking about PowerVia, and you said it will have a lot of positive aspects, especially for signaling quality, switching speeds. Do you also expect that it should be better thermally?
Well, due to the backside power routing, the whole thermal management is different than how we've traditionally done it. So again, we're developing new techniques around thermal management, both in my group as well as in Babak's group. This is sort of very jointly worked on together because it ties in closely with the full package integration. I'm very sensitive to it. It's been a while, but I used to build a new computer for myself every 2 years, taking the latest, fastest Intel chip. So I spent a lot of time thinking about thermal interface materials, bus fractions, you know, getting the max I can get without burning the whole thing out. So I have some firsthand experience with the stuff you guys are dealing with every day. My knowledge is a little dated, but I'm certainly sensitive to it.
Okay, that's cool. That's very cool. I want to go over to Forest Direct, Because that was also very impressive to me. One of the most impressive things you presented, because to me it looked like, I mean, you're bonding together two different chips, for example, and you announced it as bonding copper interconnects, like bonding copper to copper. And I was wondering, how do you do that? Is it just pure cohesion, like the copper atoms sticking together, or how is that working? Can you give more details on that?
I can do that. So basically, we had to polish the two surfaces almost perfectly with a amount of dishing on the copper. I mean, copper is a little bit recessed at the bonding area. It's about nanometers. Then we have to align the bumps together, and that's done mechanically, as you can imagine, with a 9-micron pitch. And first, the oxides fuse together, they form a strong bond, and then copper gets connected hydrostatically. And there is an oxide layer there on top of the copper when it gets dissolved there. And that's how you form the copper-to-copper bond. Actually, this concept has been around for a long time. It's not neophysics discovery. It's just a new application.
Okay, that's very impressive, especially the mechanical part you highlighted, that you have to be able to position this so precisely. That's very impressive. I have one question, which is going actually back like 2 or 3 generations of the Intel Core CPUs. Back then with the 8th generation, Intel was not using the solder TIM interface, but it was still using polymer TIM. And I'm not sure if this is kind of connected together, but back then, talking about the packaging probably, the die height was about 0.4 millimeter of the 8th generation. And after moving to the 9th generation, it increased to about 0.6 millimeter die height, and it was soldered. I was always wondering if there's like a direct correlation between the fact that the first one was polymer TIM and the second one was solder TIM, and there was an increase in die height, or is that not connected to each other?
No, there's really wasn't any correlation. I mean, we switched over to polymer TIM, and then we got a very strong message from the gamers that we switch back to STIM, solder TIM, and we did. Usually there is a special silicon thickness that would maximize your thermal performance. So we adjust the die height for that. But the difference that you mentioned between those 2 generations was not driven by solder TIM.
Okay,
it was, yeah.
That's very interesting, because that would actually, I mean, to me as a conclusion, would mean that we might be able to see like thinner dies again, or I'm not sure. At least going from 9th to 10th gen, we already saw that you were going back to thinner dies to improve the thermals correct. As well. So
that improves the thermal. That was the main reason we did that, as you correctly pointed out.
Okay.
If you go too thin, then you just don't have enough silicon volume to spread the heat. So there's a special thickness that we want to go to maximize thermal performance.
So I guess you have to find the right balance between having enough mass to transfer the heat, but at the same time keep it as thin as possible, because it's not the best conductor, I guess.
Yes.
Okay. Yeah, the next one was also about the packaging and the substrate of those chips. On the 8th gen, I also noticed that the substrate, like the packaging itself, was very thin, like below a millimeter, something like 0.9 something millimeters. And then on the later generations, it also increased. And there's usually some variation between the generations when it comes to the substrate. Is there more like an ecological reason for that, or is there like is the cost involved, or is the signaling like a priority there when it comes to the thickness? Because we saw a lot of damages, I would say, on the 8th generation and 7th generation, because the PCB was rather thin and it was easier to damage than, for example, on 9th and 10th gen.
Yeah. No, it wasn't. The change was not driven because of customer damage or anything like that. In 8th generation, we did not have the fully integrated voltage regulator. However, in the next generation after that, we went back to fully integrated voltage regulator. So that's one difference, and we needed to have the right inductance there. That sort of at times sets up your package thickness. Also, there's another factor that is really important, especially for bulkhead array packages, that we have to manage the warpage. So we could do the surface mount process. So depending on the die size, die thickness, as well as package thickness, we've got to hit the right combination there. So we have a very successful surface mount process.
Okay. Very interesting. As we already discussed, we're doing a lot of overclocking stuff in our community, and especially in the German communities. That's something I saw over the years. People are still, I think, a little bit conservative when it comes to overclocking and increasing frequencies and voltages. They're often afraid that they're burning their parts, even though I personally think that they can sustain a lot more than people usually think. Something I often read is the electromigration thing. Where you know that the traces basically fall apart over time. How is this in the latest generations? Because the information that's usually spread in the internet is like 20-25 years old, and I guess by designing your chips, you're also fighting this actively, so it's not falling apart. And can you give like some information? This is even still a thing in 2021, or?
Of course.
Let me try this one because it's more on the fab process side. Yeah. It's, of course, as Babak said, physics is still physics. It hasn't changed. Yeah. So in that sense, electromigration is still very much a thing, and I'll say, unfortunately for your audience, the physics in Germany is still the same as the physics in the US. So I wish I could make it better for you that way.
Available yet. First of all, we were talking about the difference of die height between 9th and 8th and 10th generation, because personally I had the impression that when they moved back to solder TIM on the 9th gen and we had this massive die, moving from 8th to 9th gen, then I always thought that this would be kind of related. But getting the reply from Babak, it seems like it's not the case, that the huge or like the massive die of like 0.9 millimeter compared to like 0.4 millimeter on the 8th gen was not related to the solder TIM, which I personally find quite interesting. It was more, as he said, a balance between the thicker packaging material and the increased die size. Regarding of what Sanjay said in the beginning when it comes to the new naming scheme of Intel, I also find it quite interesting that he said that Intel was actually quite open to the industry to find a solution which is like comparable to the rest of the industry, but as he said, the rest of the industry was not interested in that. That's actually quite surprising. And also regarding PowerVia, that was also very interesting. Obviously, I tried to get some more information how they're actually manufacturing it. He said he cannot really disclose how it works out, but I think just from looking at the pictures we saw, like the SEM shots, I think the only way they could manufacturing something with PowerVia would be that you first off start with your, let's say, logic die, which contains all the transistor, then you thin down this specific wafer from the back. So just behind the transistors, you make a very, very thin layer, and then you have a second wafer probably which contains everything which is power related, and then in the end you will have to bond two wafers together. That's probably the only way you could manufacture this, but I guess that's just pure speculation at this point. Maybe you have more information, then feel free to point it down below. Alright, I think it was still quite interesting. It was a different video. Thanks for tuning in and see you next time. Bye bye.